my talk today is entitled Representation Theory and Geometry. And I just want to give you a glimpse of what I think is a beautiful subject. I should begin by saying it's a real honour and a pleasure to give this lecture in honour of art. Perhaps this is not such an unusual story, but my first encounter with art was the following. So I'd heard of the art invariant, and I went on a bicycle tour along the coast of Turkey with my father, starting from Izmir and going down to Kuşadası and then nearly to Bodrum and then back up around. And I got back to Germany and I dumped like some of the Turkish lira that I still had on my office desk. And then about a week later I was thinking about something and my eyes kind of flashed over the note and I thought, oh, there's a formula on the note. And then I realized that this was art. And at that point I actually didn't know that art was Turkish. And I certainly had no idea that his formula was on the 10 lira note. So what I'm talking about today is representation theory. So we start with G is a group, and K is a field. And a representation of G is a homomorphism rho into GL of V, where V over K is a vector space. And it is simple or irreducible if the only invariant subspaces are 0 and the vector space itself. So the only invariant subspaces are the obvious ones. And what are we doing in representation theory? We're trying to, one should imagine G as being some problem in mathematics or some structure in mathematics, and what we're trying to do is understand it in a concrete way. For example, if we choose a basis of V, then this is just the same thing as assigning every element of your group a matrix such that the multiplication of matrices reflects the law of the group. So why are we doing this? I remember when I was a third year student and someone first told me what representation theory was, I thought, okay, this is the story that I invented for myself. I thought, mathematicians are interested in finite groups. The obvious thing to consider is an action on a set. And what mathematicians have done is they've gone and solved that, and now they still need a job, and so they invent a complicated problem, action on vector spaces. And that's why they're studying representation. But this is not at all the case. So if you look at a finite group action on a set, this is very, very complicated. For example, actions of symmetric groups on sets are the same thing as subgroups of the symmetric group up to conjugacy. And this is very close to the question of understanding all finite groups, which we're very, very far away from. So this is some question which is both difficult enough to have a highly non-trivial theory, which is very useful, but simple enough that we can have a nice theory. So probably the most important example of this is when G is the circle group. So these are those complex numbers of law 1. Then the simple representations up to isomorphism are parameterized by z, and so an integer m goes to the homomorphism that sends z to the n. Okay, so this is an element of my group, and I want to associate this a 1 by 1 matrix, which is this 1 by 1 matrix. Okay. And you probably remember from the theory of Fourier series that L2 of S1 that these are the fundamental frequencies of Fourier analysis. When you first see Fourier analysis, you see Fourier series, you see sines and causes, but actually what's hiding there is the complex numbers. And so this is the irreducible representations are the fundamental frequencies of Fourier series. A second example would be R under addition, and this leads to the Fourier transform. Or we might take SO3, and this would give us the theory of spherical harmonics. So this is the analog of Fourier series, but for the sphere, for the two spherical harmonics. So in general, one should think about the irreducible representations as being the fundamental frequencies of your situation, whatever that means. So I hope that many of you have seen that quantum mechanics is very closely related to the representation theory of SU2. So for example, the fact that quantum mechanics is SU2 and rather than SO3 is the notion of spin of an electron, spin up or spin down. I'm very interested in the work of Hermann Weyl, and he explained why. So he developed the representation theory of a compact Lie group, generalizing the case of S1 and SO3. And he was asked what led him to do this. So this was in the 20s. And he said, so I think this quote is from the 1950s. He said, "The wish to understand what really is the mathematical substance behind the formal apparatus of relativity theory led me to the study of representations and invariants of groups." So he was interested in what is really going on in relativity theory, and this led him to representation theory. So you have representation theory very closely connected to quantum mechanics and also relativity theory, general relativity theory. And another important application of representation theory is in the Langlands program. So you can see, I think you can make an argument that the most fundamental discovery of the 20th century in physics was the discovery that symmetry underlies physical law. The Langlands program is the statement that symmetry underlies much of number theory. And whereas in quantum mechanics and in general relativity, you have groups like SO3 or SU2 or reasonably easy groups, in the Langlands program you have non-compact real groups like SL2R, and you also have p-adic groups. But still that idea that they're irreducible representations are the building blocks is there. Okay? So for the rest of this lecture we'll be considering finite groups. So we take G a finite group. And here we have a real dichotomy, which is if the characteristic of K does not divide the order of the group. So remember, so for example, if my field is the complex numbers, then the characteristic is 0. But my field might be, for example, a finite field, in which case the characteristic is a prime number P. If the characteristic does not divide the order of the group, then the representation theory is semi-simple. So this is what people often call complete reducibility. And we have that the number of irreducible representations, number of simple representations, is the same thing, the same number as the number of conjugacy classes. Okay. And here, I guess, from now on, I should also assume that K is algebraic. And the connection between these two, so this number is the same, but there's no canonical bijection between these two objects in general. And one should think about the way of moving between these as being the character table. Which is a kind of non-abelian Fourier transform. So whenever you have a function on the circle, it makes a lot of sense to decompose it into its Fourier coefficients. If you have a function on a finite group, and if it's conjugation invariant, then it makes a lot of sense to decompose it into the characters of your group. And if the characteristic of K does divide the order of the group, this is not semi-simple, never semi-simple. And one has a number of simple reps is the same thing as the number of P regular conjugacy classes. So that these are those conjugacy classes such that any element in that conjugacy class has order not divisible by P. And this is a very well understood theory, and I would say that it's extremely useful because it is not a difficult theory. Whereas this, here there are many open problems, and I would say that here it is useful because it is difficult. It's useful because there's very, very rich structure here. Just to give you an example of a question here that was recently resolved but is extremely deep, the so-called Cahit conjecture from 1972. I think, yes. So the number of, so if we denote by P inside G, a C log P subgroup, the number of simples, simple reps of G of dimension co-prime to P. So this is something that, so for example, you can go to the library, you can look at the atlas of finite simple groups, and you can look at the monster simple group and see how many representations are there whose dimension is not divisible by, sorry, this is 2. So odd dimensional. It should be the same thing as the same number for the normalizer in G of P. So this was recently solved by Muller and Speth, but it seems to be an extremely deep fact about finite simple groups, and their proof, for example, uses the classification of finite simple groups. And this statement is still open for P not equal to 2. So a very basic problem about finite groups that we certainly do not know the answer. And I just want to give you some kind of analogy. So in the title I have representation theory and geometry. So if we fix G, so as the characteristic of K varies, there's only finitely many interesting cases. And the rest is uniform. Now, I want to compare that with a similar situation in topology, where if we have X a finite, let's say, a space of finite type. So, for example, a complex algebraic variety or a finite CW complex or something like that. Then we have the cohomology is the same for finitely many characteristics, and this is kind of controlled by torsion. So if you know the universal coefficient theorem in topology, it tells you that you can deduce the cohomology of X over any field from the cohomology of the integers. Because it's a finite space of finite type, there's a finite amount of torsion in that cohomology, and it's only for those torsion that interesting behavior will show up in the cohomology. Controlled by. And so I won't have much time to go into detail about why this is a very fruitful analogy, but many questions in representation theory we kind of attack by translating some question about cohomology and torsion in cohomology. Another example of where this analogy is fruitful is in number theory, where you have some extension of fields, so something that Arf probably spent half of his life thinking about, and you only have finitely many ramified primes at which there is an enormous amount of information, and the rest are somehow uniform. So now I want to switch to the symmetric group.
How is the Cahit conjecture solved? Something simple with spaces? Or?
So the Cahit conjecture is very... So to answer your question, there's some very complicated statement about quasi-simple groups, which are much more complicated than this statement. And people show that if you could show this statement, then you could show the Cahit constant, the Cahit conjecture. And then these statements were verified case by case for a long list of simple groups. And a remarkable aspect of this. So this paper is you can download it. It's just freely available on the internet. It's about 2.5 pages long, and he makes this conjecture, but for some reason he doesn't even mention the fact that it might be true for another prime other than 2. Which I find absolutely remarkable. So he notices this amazing thing and checks it in various cases. So he checks it, I think, with symmetric group. But then afterwards, everyone said to him, "But what about P not equal to 2?" And he said, "Oh, I'll check." And then it also seems to be true. But there we have no proof. Okay, so now I want to focus on the. So this will come up a little bit towards the end. This analogy. It's just something to bear in mind. So I want to focus on the symmetric group. Where are the erasers? Now we focus on the symmetric group. Okay, which is probably, if you had to vote for the most fundamental of all finite groups, this one would get my vote. So over C, we have that the simple representations are in bijection. Now that bijection is canonical with partitions lambda. Okay, so this is a sequence, an increasing sequence of integers. And so, for example, the trivial representation corresponds to this partition, which I'm just writing as n0. And the sign representation, the sign of a permutation, corresponds to this. And now, if you've never seen the representation theory of the symmetric group, there's an absolutely extraordinary paper by Akunkov and Biashek, which is very worthwhile reading. And I just want to explain in about 5 minutes what they do. So what they do is they consider the representations of the symmetric groups, but for all n at once, as a big tower. So they look at rep CS1, rep. So the complex representations. Etc. And on these, you have natural induction and restriction functions. So the symmetric group S2 sits inside S3 in a natural way as the permutations of the first two elements, and we can induce. And we can also restrict. So this is just the representations of the trivial group, so this is the same thing as C vector spaces. So the remarkable thing here is that the passage to the growth, so if you consider, so let me just give you, so there's some beautiful combinatorics underlying this whole picture. So an example, if I look at the restriction from, so this is an irreducible representation of the number of boxes here, which is 1, 2, 3, 4, 5, 6. So this is an irreducible representation of S6. And when I restrict it down to S5, I can ask what irreducible representations do I get? And the answer is given just by removing all ways to remove a box so that you still have a partition. Okay, so this is... And what they explain is that if you, all of this combinatorics of how you restrict and induce is encoded in a representation of the Heisenberg-Lie algebra, which is very important in theoretical physics. And you can explain the whole theory of the representation theory of the symmetric group, namely this. So you don't need to assume this classification. You can deduce it from this. And you can deduce the whole theory of standard tableau and character formulas and stuff, all from this very simple picture. So now we go to the case of modular coefficients. So representations over a field of characteristic P.
So in this picture you explained what is one map and what is another map?
The other map is always to add a box.
Where?
So the induction
Everywhere.
of, yeah, so let's say this one is always all legal ways to add a box. And It's one of these things that's both disarmingly simple but disarmingly powerful, this picture. It's really very, very beautiful. So now in the modular setting, so now K is FP. So this induction functor, or actually restriction functor, so let's call E our induction functor and F our E our restriction functor and F our induction functor. And it turns out, so this is a functor, and you can decompose it into as a sum of subfunctors. So EA, and these are indexed by elements at FP. And similarly, we can decompose this as a sum of subfunctors. Now that sounds very complicated, but all that I'm saying is that if I apply this restriction functor to any module, then this module has a canonical decomposition indexed by elements of the finite field. And I call these pieces EA of that module. And now the remarkable thing is that on Grothendieck groups, so if we look at what's going on at the level of combinatorics, we get a so-called Fock space. So I don't expect you to know what this means, a Fock space representation. So this is an affine Lie algebra, which is again extremely important in mathematical physics. It first came out of conformal field theory, for example. And remarkably, and this Fock space is somehow the most beautiful module for this. It's a big infinite dimensional module, and it's the most beautiful module for this affine Lie algebra. And remarkably, this is also showing up in the mod P representation theory of a symmetric. And then we have something called James conjecture, which is that the classes, so if P is bigger than the square root of n, the classes of the simple FTSN modules are given by distance. So again, I'm not expecting you to know what these words mean, but I just want to give you some feeling for what this statement is. So if we look at a symmetric group in characteristic P, we know essentially nothing about the dimensions of its irreducible representations. We know how many there are, but beyond that we know very, very little. It's an embarrassing fact, I think, in mathematics that we still haven't solved this problem. But it seems to be extremely difficult. And what this conjecture is saying is that inside this Fock space representation, so something that came from a completely different world, there's a particular combinatorially defined basis that's rather easy to compute. It has enormous subtlety, but you can compute it on a computer very quickly. And this conjecture is saying that as long as P is not too small, this basis is the basis of simple modules. So that if this conjecture is true, then we can answer a fundamental question in representation theory for many P. And the suspicion is that when P is very small with respect to n, then kind of all hell breaks loose and we'll need another 100 years. And this is okay for n equals 2, 3, 4, up to 22. But in 2013, I show that this is false for n starting from 10 to the 6. So basically we know very little. There's some statements in representation theory that kind of start off looking like they're okay, but then once you get up to very, very big symmetric groups, suddenly things don't go as hard. So I just want to explain a little where this comes from.
Couldn't you kind of use the Cartesian lines to decide how many symbols you have? So looking at the orders of the partitions.
So this rule is valid in characteristic 0.
But you still have the prime element for correspondence between symbols and the K and the P prime order.
Yes.
So the partitions I can decide which ones are different.
Yes, you can do this definitely.
Does it give you these decomposition? Like how do you interpret this right word in terms of X?
So essentially, so what I forgot your name. I'm sorry. Edwin. What Edwin is saying is that we still, so in the mod P world, we have a characterization of simples as certain partitions. And what does these certain partitions mean in this world? And the answer is that they're given, so this Fock space module is not irreducible, and it has some irreducible quotient, which is exactly projecting onto these symbol representations. But so this Fock space has an obvious basis given by all partitions. But one should say that the obvious basis has nothing to do with the basis of simple modules. So in characteristic 0, the obvious basis just is the basis of simple modules. But in characteristic P, there's some very complicated combination of this obvious basis that gives you the answer that you want. So I just want to briefly outline the connection to geometry that allowed this theorem to take place. So the connection geometry is the following. So we can consider Q the following quiver. Okay, a quiver is just a fancy name for a directed graph. And we assume that there's P vertices. Now, what we can consider is rep Q, which is the space of representations of Q in C vector space. So, just an example, if P is 1, so this means that Q is just one point with an arrow going back to itself, then rep Q is the space of V plus space of your quotient. So it's pairs Vx, where x from V to V is no quotient. And if you choose a basis for your vector space at each vertex, then you can see that this is very naturally a space and in fact an algebraic variety. And now yeah, I mean, technically speaking, it's a stack, but it's something like algebraic, right? And so now there's this remarkable theory called higher representation theory. So if you imagine representation theory, it's the question of imagine that I have a vector space with certain symmetries. What can I say about that vector space? For example, the vector space might have symmetries given by a group, or it might have symmetries given by an algebra, might be representations of the algebra. What can we say about that vector space? So a simple example is imagine I have a vector space acted on by the monster simple group. Then either the action is trivial or this vector space is at least of dimension 17,000 something. Kind of remarkable that just knowing certain structure on your vector space already tells you a lot about your vector space. So that's what representation theory is. What is higher representation theory? It's the idea that very often in mathematics we have a certain category with some form of symmetry. So this is a classic example here. Here we have a whole lot of categories, and we can take their direct sum, and then we get some kind of symmetries of these categories, and we can ask, what can we say about a category with symmetry X? And that's what higher representation theory does. And what higher representation theory allows us to do in this particular case is relate these two problems. So what it tells us is that if we look at sheaves with FP coefficients on, I wanted to call this nil. So nilpotent representations. Then this category actually controls the direct sum of all these representation categories. That's the metric. And there's a long list of names that goes behind this theorem, and I don't want to list a whole lot of names, but what this allows us to do is take questions in this representation theory of the symmetric group and convert them into questions in the geometry of nilcubed. So maybe I have time for a tiny example. So when should I finish? Around about 5. So just a really simple example of this is if we look at C2 together with a nilpotent endomorphism. So we can write this as a matrix, A, B, C, D, and X nilpotent is the same thing as its eigenvalues are 0, which is the same thing as the trace and the determinant are 0, which gives us that A is equal to minus D, and minus A squared minus BC is 0. And so this space of C2 with an X nilpotent is the same thing as the set of minus A squared minus BC equals 0 inside C3, which is a quadric cone. And now the so-called link here, which is, so let's call this X. This is X intersected a small free ball. So this is sitting inside, a small eyeball. So this is sitting inside C3, which is real 6-dimensional. And inside of a 6-dimensional space, you can imagine a 5-dimensional sphere, which I call S5 epsilon. Now, this little 5-dimensional sphere intersects X. It's a nice exercise. Is RP3. And if you go through all of this very, very high-level mathematics, very crazy stuff, the very easy fact that S2 is not semi-simple is equivalent, in fact, to the fact that there's only two torsion in the cohomology of R. Which is kind of like this. We could give it as an exercise. So this is not interesting information from a representation theory point of view, but in other situations, you go right across all of this crazy stuff, and then you come down to a calculation like this that you can actually do, and then suddenly you have some new information in representation theory that you could never calculate. Okay? And that's how these kind of counterexamples come down.
So in this example, instead of taking complex, you could have taken the real.
Yes, I could have. Yeah. Okay, so now I want to show you some slides. In a sense, let's turn on the slide. So I will just outline the crucial problem. So I'll leave the boards for 2 more seconds. Sorry. And then I'll show the slides. So the crucial problem is the following. So in S lambda, so this is an integral module of an irreducible representation of Sn of Sn so this is a so-called okay. So the irreducible representations of the symmetric group are parameterized by partitions, and we can realize them all over the rational numbers. But it turns out that we can actually represent them as integral matrices. And when we have some integral matrices, then we can reduce these matrices modulo P. And the key question is how does this decompose into simple representations? Simple reps. So if we could answer this question, then we would have solved this question of describing the simple representations of symmetric groups in P. And what I want to show is a video, eventually, of a conjecture, a recent conjecture with Lustig on the 3-row case. So, when we do this, and we take an irreducible representation with only 2 rows, it turns out that only irreducible representations with 2 or 1 row can occur. So the first case would be the trivial representation. So when we reduce this modulo p, this is really easy. So what I'll show first is the case of 2 rows, and then the case of 3 rows is still open, and I want to show a video illustrating a conjecture. Okay, so let's hope I can use it. Okay. Thank you. So this is a picture illustrating the decomposition pattern of irreducible representations, of 2-row irreducible representations when the characteristic is 3. So what this is saying, so in the 2-row case, you can encode everything instead essentially as a single number, which is this gap here. And this is a picture illustrating the answer, and so this is a known theorem. But I think you'll agree that even in this case, you get a beautiful kind of fractal-like structure. So what we get, you can guess, so in this particular case, this is the answer for p equals 3. But you can guess what the answer looks like for all primes, and you can also guess how it continues. And it's not, even in this very simple case, it's not so trivial. And so what we're kind of hoping to find in the next years is this kind of fractal structure, but deeper in the symmetric groups. So now I don't want to explain how we do this, but when we reduce certain, the most important, so the most difficult question is how often does the trivial representation occur when we reduce modulo? So the trivial representation is one-dimensional, and you can imagine that it's kind of subtle how many times that one-dimensional module occurs in a composition series. And these are, so in this particular case I'm looking at n equals 12, and these are all the irreducible representations for n equals 12 that can possibly involve the trivial representation when I reduce modulo p. These are the only ones that can possibly have a trivial representation, and once I've solved the case of the trivial representation, we're done. And I'm not explaining to you why we're done. And so now I want to give you an example of what, this is actually what we compute. So we draw the following pictures in which we write numbers in these outcomes. And what these numbers are telling us are, like if I take this particular irreducible representation, this particular S lambda, and I reduce it modulo 3 in this case, then the trivial representation occurs in that precisely once. And up here, we have that it's occurring twice. So now I want to show you, so basically over the last 4 or 5 years, we developed a new way to calculate this. So it's extremely difficult to calculate any more numbers that are basically present on this slide. And we developed a new way to do this in coming from these techniques that I'm talking about, so higher representation theory and geometry. And it led to a particular algorithm, which I then implemented in Magma. And this algorithm involved several, like about 30,000 lines of code or something, which we then ran on a supercomputer in Bonn for 10 months. So we ran a supercomputer in Bonn for 10 months, and then it gave the answer, and about 2 weeks later the computer crashed. So it was incredibly lucky, and since then we've never managed to get a computation going in more than about 2 months without it crashing. We don't understand why. Okay, so I want to, so this is what the thing is. And what this is telling us, what these slides are telling us, is here I have some absolutely ginormous symmetric group. It's probably something like so this is p equals 17. I don't know, I'm guessing, but this is probably some symmetric group of the order of several hundred. And what we're looking at is where do trivial modules occur? Which modules, when we reduce to mod p, have a trivial module in them, and when they do, we put one of these dots. And this is what you get. So this is our conjecture, and it seems absolutely remarkable that this is described, it's conjecturally described by some discrete dynamical system in which balls are bouncing around in upright. And it seems absolutely remarkable to me because you really can't imagine a more algebraic discrete problem than mod p representations of symmetric groups. And yet there seems to be some kind of continuous billiard-like behavior in them. So I'll just leave you with the video, and thank you very much.
Any questions? Very nice questions, since you mentioned all physics. In physics, most useful representations are projective representations in quantum mechanics. Do you consider these at all, or are there projective representations?
So you probably saw this little hat on the SLT.
Yeah.
So this is the fact that this is actually, so it's secretly a projective representation of the non-centrally extended SLT. So in all of these Grothendieck groups, they are more natural, well, they're projective representations or actual representations of some central extension. But the central extension is absolutely key. So like that Fock space, for example, is invisible if you don't allow projective representation.
So we consider centrally extended groups.
Always, yeah. And we're dead if we don't.
Any more questions? The James conjecture with these big computations, is it from the 10 to the 6?
So these so the James conjecture, there's this P is bigger than square root of n. And in this particular case of three-row partitions, this is saying that there's only one law in this billiards. And so in some sense, the James conjecture is predicting some kind of generic behavior, and when we're doing this billiards conjecture, we're doing it in a different region that's not at all covered by the James conjecture. But it's by related methods that I was able to find these enormous
Second question. You explain this by with RP3. So what the conclusion line here? RP3 has told you, but that gives you some kind of fact that doesn't have just line models. That's why it's not.
Oh, what is the?
So what is the conclusion?
So the technical answer to that is, if we blow this up, we get a minimal resolution at this surface singularity. And the statement is that the decomposition theorem fails when 2 is not invertible in your coefficient. So there's some statement called the decomposition theorem in algebraic geometry, and it's precisely the correctness of that theorem that is governing whether something like the James conjecture holds.
So somehow this confidential feature looks like your operation look like operation in homology of Grassmann multiplication by C1.
Yes.
And somehow, is there any meaning, any explanation of that? What is the relation of this presentation to Grassmann? How it comes?
So there's two answers to that question. It's a very good question, by the way. So perhaps some of you know that these also index bases of the cohomology of the Grassmannian, and this operation of adding a box is precisely multiplication by the first Chern class of the determinate bundle on P1. And so if you go through this higher representation theory point of view, you can actually develop an equivalent picture with grass values. So that's the first answer. But I think the second answer is I don't think we really understand properly why. So Kumar has done recent work on this. For example, as soon as you leave the symmetric group and go into other types, we don't really know. Well, maybe Kumar knows, but we haven't yet digested what he's saying.
More questions or comments? Okay, if not, let's start our speaker again.